We have several rules when it comes to writing chemical formulas, and those rules will depend upon the type of bond we're dealing with. So in this case, we're going to be talking about ionic compounds. Ionic compounds are metals and nonmetals. When given the name of the compound and asked to write the formula, you have to think about the charges of the metal and the nonmetal. We do this process called the crisscross method. In the crisscross method, we take our charges that are superscripts, and we just bring those numbers down and switch places. So for example, here we have Pb4+, so this would be lead 4, and then oxygen 2-. So we would bring the 4 down behind the oxygen and the 2 down behind the lead. We do not write charges when writing ionic compounds. So by bringing down the 2 and the 4 and switching places, we end up with a formula of Pb2O4. Ionic compounds, however, are always the lowest whole number ratio. So we can reduce this to PbO2. So this would be the formula for this compound. If we have a transition metal or lead, bismuth, or tin, we have to use Roman numerals to tell the charge of the metal. So for example, this guy right here would be written as lead, Roman numeral 2, Roman numeral 4, oxide. That tells me that the lead has this 4+ charge. A polyatomic ion is a group of atoms with an overall charge. And if there are multiple polyatomic ions in a compound, we have to use parentheses with the subscript on the outside, showing that there are multiples. So let's do some examples. So first off, we have a cation of Cu+ and O2-. So to name the material, to name an ionic compound, we name the metal, which in this case is copper. Copper is a transition metal, so it requires a Roman numeral. So we look and we see that the charge is +1, so we would say copper 1. Now we name the nonmetal. In this case, it's oxygen. Drop the ending and add IDE, so this becomes oxide. So this would be the formula if we have the cation of Cu+ and O2-. So if we're going to do the formula, if we're going to construct the formula, we're going to do the crisscross method, which means I take this 1 and I bring it to the back of the 2, and then I take this 2 and I bring it to the back side of the Cu. So my formula would then be Cu2 O. So what this says is I have 2 copper 1+ for every 1 oxygen 2-. Since oxygen is 2-, I have to have 2 positive charges to cancel it out. All right, let's look at this next one. Here we see we've got Cu2+. So this is different than Cu+. So we say copper, Roman numeral 2, oxide. So these are different compounds. Even though they both contain copper and oxygen, they are different compounds with different properties because that copper has a different charge. So the formula, if we do the crisscross, we bring this 2 down and this 2 down. And when we do that, we end up with Cu2O2. But that can be reduced to CuO. Iron 2 chloride, that tells me that iron has a +2 charge. That's what that means. Iron 2 means it has a +2 charge. Now, chlorine is over in group 7, which means it has 7 valence electrons. It wants one more. So it's going to gain 1 electron, meaning it now has a -1 charge. So the formula would be, if we do the crisscross, we'd see it is FeCl2. We need 2 chlorines to cancel out 1 iron. The next one, Fe3, so iron 3, meaning iron has a +3 charge. Chlorine is still the same, -1. If we do the crisscross, we bring the 3 down to the back of the Cl, the 1 to the back of the Fe. We see our formula is FeCl3. Next, sodium phosphate. Sodium is in group 1, so it has 1 valence electron to get rid of. That means it has a +1 charge. If we do the crisscross, we see we take this positive, this 1, we bring the 1 down here, and we bring this 3 down here. And so I see I now have Na3PO4. I have to have 3 sodium for every 1 phosphate. Now, what's going on is phosphorus has 4 oxygens attached to it. Each of these oxygens is now going to have a sodium, or not, I'm sorry, not each of the oxygens. The oxygens with the single bonds are now going to have these sodium ions with it. So remember, sodium is positive, and these oxygens are going to be negative here. Right? That's where that -3 charge comes in. So this is why we have to keep this 4 attached to the oxygen, because there are actually 4 oxygens attached to this 1 phosphorus here. So that's why we say Na3PO4. All right, this next one, NH4, this is a polyatomic ion called ammonium. That's just one of the ones you'll have to learn. And then Cl-. So we name the element chlorine, drop the ending, and add IDE. So this becomes ammonium chloride. When we write the formula, again, the 4 is attached to the H, so it sticks with it. So we say NH4Cl. And then our last one here, aluminum sulfate. Aluminum is in group 3, so it has 3 valence electrons. It's going to lose those 3, so it will have a +3 charge. So we bring the 3 down and the 2 down. And I see now I've got Al2, parentheses SO4, parentheses 3. This tells me I've got 3 of these SO4 particles. So because there are more than just 1 of these SO4s, I have to use parentheses. Next is metallic bonding. So metallic bonding involves what is called the sea of electrons. So electrons are not tied to individual nuclei of atoms. They actually just kind of go all over the place. So they'll spend time with this metal cation, and then they'll go to this metal cation, and this one, and over here, and then up here, and they're moving really fast, and so much so that there's really not just a single electron attached to a nucleus. They're just shared completely throughout. So we call this the sea of electrons. And it's this sea of electrons that gives metals their properties. So metallic bonding, surprise, involves metals. Metallic bonds form together in this nice repeating structure called a lattice. They are solid at room temperature, except for mercury, which is a liquid. They have low to high melting points. So mercury is very low, but tungsten is extremely high, over 3,000. Their boiling points are extremely high. They are conductive at any state, and they are malleable. So they're conductive because of these electrons that are free to move around. If we can get these electrons to move in a single direction, we call that a current. When we have metals together, we can see them in a couple of different arrangements. As the pure metal, that's just going to be a single type of that atom. So things like aluminum, iron, so any of those pure metals, any of those just straight up elements that we would see on the table. So we're going to show what that would look like, the particle diagram for these guys. So I'm just going to make some atoms or some particles. And I'm just going to keep making these and have them be really close to each other and on top of each other. Because again, metals have this nice repeating structure called the crystal lattice. Okay. There we go. So that would be an example of a pure metal. Everything is exactly the same. So the same type of atoms, and they're nice and neatly organized. Well, a substitutional alloy. So an alloy is a homogeneous mixture, meaning it looks the same, of different metals and sometimes a non-metal. So substitutional alloys means that you have new atoms replacing the original metal atom. And the substituted atoms are typically the same size or very close to the same size. So I'm just going to change the color of some of these to let us know, hey, they're pretty much the exact same size. And even though I'm changing some of them, they're still going to continue to have the same metallic properties. So these would be something like copper and zinc. Copper and zinc are almost identical in size, so they can substitute each other very easily. The last alloy is called interstitial. Interstitial alloys have small non-metals in between the large metal cations, the large metal atoms. So I'm going to make a teeny tiny little non-metal atom, and I'm just going to move it in between. Right, so we can see that there are some spaces in between those large metal atoms, spaces where some teeny tiny little baby non-metal atoms can slip right in. Okay? And this is going to disrupt some of the chemical or some of the metallic properties, but not all of them. So for example, steel. Steel is made of iron and carbon. Well, carbon is very small compared to iron, and so it just kind of worms its way in between those metal atoms. And this is going to cause the iron to become harder. It's less malleable because those carbon atoms kind of get in the way. When you try to bend it, there's now like something that's preventing it from bending all the way. But they are still going to maintain the properties of being conductive and being magnetic because it's iron. So alloys will have the same metallic properties that we expect, so malleable, conductive, whatever. It's just they might have a couple of different metals in there, or maybe even a small non-metal. All right. So there's your homework for section 2.